Now that we've looked at some of the basics of rotational kinematics, we're now going to start looking at situations where we have a combination of both rotational motion and linear motion. And there's two major cases that we're going to look at. The first would be an object rolling along a surface. So think about a ball rolling along a floor, a wheel, something like that. When that's occurring, okay, the object itself is rotating, all right, at the same time that it's traveling forward. The center of the object as a whole, is traveling forward, okay, so as it rolls along the ground. And in that situation, we're going to have both angular velocity due to its rotation and linear velocity, which we're going to call the translational velocity. So that's really the velocity of the center of mass of the object, of the wheel, of the ball, of whatever it is that is rolling along the ground. The second case we're going to consider is a stationary object that's spinning or rotating in place, and we can think about a point or even another object that's sitting on this rotating object. So we have our spinning disk here is shown, and we're going to maybe think about this point here and think about the angular speed of the disk as a whole compared to the tangential velocity of this object on the disk, which ultimately is going around in a circle. A great example of this would be like a merry-go-round or a carousel, right? The carousel as a whole is spinning, and so we can think about the angular velocity of the carousel, but also if we look at any object, like a child on one of the horses on the carousel, we could think about their tangential velocity as they travel around in a circle on this rotating carousel. The good news is, in both cases, whether we're talking about the translational motion of a rolling object, thinking about the velocity of its center of mass, or the tangential motion of an object on a rotating platform or something like that, the link between the angular quantities and the linear quantities is the same, and that link ends up being the radius of the circle. Every single time, if we take the radius of the circle times the angular quantity, delta theta, omega, alpha, it gives us our linear equivalence. One quick note that we do need to make is, you see this asterisk here, when we're talking about the case of an object on a rotating object, so we think about this point, okay, going around in a circle on a carousel or something like that, we know when we go around one full time, the displacement is 0. Okay, so what this actually gives us is not truly our displacement. What it gives us is our distance traveled. All right. In order to be consistent with everything else, I left it as delta x, but really you should know that that's the distance traveled. Now, if we're talking about a rolling object and we're thinking about how much a wheel rotates compared to how far it travels horizontally, then it truly is a displacement. But it doesn't quite work for the object on a spinning object, but I left it that way, again, like I said, for consistency. Let's go ahead and do a few quick conceptual questions here with this. So for this first one, we have a record that's spinning, and there's two flies sitting on it. We have fly A and fly B, and we can see that fly B is sitting closer to the center of the record than fly A. And we want to know which one has a greater angular speed, which one is changing its angular position at a greater rate. So what I would think about is, let's think about A making one full trip around the record like that. In the time that it takes A to go around the record one full time, an angular displacement of 2 pi, B also makes one full trip around the record because they're rotating, they're spinning at the same rate. So these two flies have the same angular speed because when the record rotates once, each fly undergoes an angular displacement of 2 pi. Which one has a greater tangential speed? So now we're thinking about their forward velocity tangent to that circle. Well, we know that tangential speed is equal to r omega. Since they have the same angular speed, okay, fly A is going to have a greater tangential speed. It's going to be traveling faster. And that makes sense too because we just talked about how when fly B goes around once, fly A also goes around once. So even though their angular displacements are the same, A has to travel a greater distance because it's further from the middle. So it makes sense that it'd be going faster. For the second question, we have this old-timey penny farthing bicycle that has two different size wheels here. And we want to know which wheel has a greater angular velocity. So we keep in mind that the wheels, since they're all moving along with the bicycle, have to be moving at the same linear velocity, the same rate, okay? But if we rearrange our equation, that link between linear and angular, we see that the angular speed is the linear speed v, which is the same for both, over the radius. So that means that the smaller wheel here with a smaller radius is going to have a greater angular speed, and the bigger wheel with the bigger radius is going to have a smaller angular speed, because the angular speed and the radius are inversely proportional. That also makes sense that the smaller wheel would have to spin faster, because when the big wheel goes around one time, that small wheel is going to have to go around many times to travel the same distance. So that ultimately means that the angular velocity of the front wheel is less than the angular velocity of the back wheel. All right, we're going to go ahead and do a practice problem here, working with this link between linear and rotational quantities. And so we have a vector that accelerates from rest to an angular speed of omega over a period of time t. We know the radius of the record is r, and we first want to find the tangential acceleration of a point on the edge of the record. So that's a linear acceleration. However, I'm given mainly angular quantities. Here's what I'm going to do. I'm not worried about that right now. I'm going to just set up my angular kinematics using what I know. And I'm going to solve for my angular acceleration, because I know that if I have that angular acceleration, I can very easily find my linear. So my angular acceleration is just going to be equal to omega over t, and once I have that, I can solve for my linear acceleration, because I know that linear acceleration, in this case a tangential, keep in mind that that equation solves for both tangential or translational, depending on your situation. That linear acceleration is just going to be r times my angular. So that tangential acceleration of a point on the edge of the record is just going to be r omega over t. So for the second question here, I'm going to use this same setup and the same basic idea. I'm going to solve for my angular stuff and ultimately find how far linearly a point on the edge of the record travels during this period of time t. So I'm first going to solve for delta theta using my 1/2 omega final plus omega initial times t, and that means that my angular displacement delta theta is just going to be omega t over 2, because that omega initial is 0. Now that I have that angular displacement, I can find my linear displacement, and that's going to be the distance traveled around this record. Okay, and so that is just going to be the distance. I'm using displacement, but really it's distance, is equal to r delta theta, and so the distance traveled is going to be r omega t over 2. For this next problem, we have a disk that's rolling smoothly along the ground and is rotating at an angular speed of omega as it rolls along the ground. And we want to think about the velocity of a point on the disk at 3 points: at the top of the disk, at the center of the disk, and at the bottom of the disk. We want to derive an expression for their velocity relative to the ground. So not relative to the disk, but relative to the ground. And we're going to consider both the translational motion and the tangential motion of this. So the first thing I'm going to do is I'm just going to derive an expression for the translational motion, and that's going to be the motion of the disk as a whole. Okay, that's what that translational velocity is. And so that's going to be equal to omega times our radius. So that means that each one of these points has a translational velocity going to the right of omega r, because the disk as a whole is moving to the right. The other thing we want to consider is the tangential speed of that point, okay? So if this disk wasn't moving as a whole, if it was just rotating in place, we would have a tangential velocity at A. We'd have a tangential velocity at C for that point, just due to the rotation of the object alone, okay? And so let's go ahead and figure out what that tangential velocity is. So for A and C, the tangential velocity is going to also be omega r. Remember, it's the same length. And so at A, that omega r is going to the right, okay, because it's rotating this way. But when we get down to C, that omega r is going back to the left, again, because it's rotating clockwise here. In the middle, okay, our tangential velocity from this point, all right, and again, we're thinking about if it was just rotating in place, there is no tangential velocity in that middle point, because if we're thinking about its rotation only, all right, there is no radius there. So our tangential velocity there is just 0. Okay, and so if we're thinking about our overall ranking here, our velocity at A is going to be the translational velocity omega r plus the tangential velocity because it's going the same direction, so 2 omega r. At B, we just have the translational velocity, so it's just going to be omega r. And at C, we have the translational velocity going to the right and the tangential going to the left, which means that our speed at C is 0. And that makes sense. Relative to the ground, that point here that's in contact with the ground is not moving at that instant. Okay? It just makes contact with the ground and then lifts back up as the wheel continues to roll. All right, so we're going to bring back another thing that we talked about earlier in the year, and that is circular motion. So imagine this situation where we have a child sitting on a carousel. So the carousel is going to start from rest and it's going to speed up. We'll say our child is here and the carousel is speeding up that way. So we have an angular acceleration going around, okay? Is the child accelerating in this case, and if so, in what direction? Well, if I had asked you this question a few months ago, you would have told me that the object's moving in a circle, so there's an inward acceleration, a centripetal acceleration, and you would be correct. However, we've also now talked about this other kind of acceleration, and that is the tangential acceleration that results from an object speeding up or slowing down while rotating in a circle. And so, in addition to that centripetal acceleration, we also have a tangential acceleration. So there's actually going to be 2 accelerations for this child. A tangential acceleration, which results from speeding up or slowing down, and a centripetal. When we talked about this before, we limited ourselves exclusively to constant speed situations, and so this one went away. There was no tangential. However, we're now going to begin talking about that, and so we will have to begin considering that tangential acceleration. So summarizing this, all objects traveling in circles have a centripetal acceleration, okay, have an inward acceleration when they're traveling in a circle. In addition, if an object is speeding up or slowing down while traveling in a circle, it also has a tangential acceleration. Okay, so the tangential acceleration is given by at equals r alpha. Okay, that's our tangential acceleration, and that just comes from those links we talked about before. The centripetal, okay, can be found with our tangential velocity, v squared over r, and we did that before. Or we can keep in mind that v equals r omega. We can substitute that in, and we get this new equation here for centripetal acceleration in terms of our angular velocity. All right, so those are the 2 equations we're going to now have for centripetal acceleration. So taking a look at this visually, and all of these assume a clockwise rotation. If we have an object that's speeding up while traveling in a circle, we're going to have that inward centripetal acceleration. We're also going to have a tangential acceleration, which is in the same direction as the tangential velocity, which leads to us speeding up. If we're traveling in a circle at a constant speed, we no longer have that tangential acceleration. We just have the centripetal, which we always have when we're traveling in a circle. And if we're slowing down while traveling in a circle, we're going to have our centripetal, and our tangential is going to be going in the opposite direction of our tangential velocity, which leads to slowing down. Let's do a quick practice problem here. So we have a carousel that's rotating at a rate of 2 radians per second, and we have a child with a mass of 30 kilograms that's sitting a distance of 1.2 meters from the center of our carousel. We want to find the net force acting on the child during this time. So we're going to be thinking about good old F equals ma. That hasn't gone away. That will never go away. So I'm solving for the sum of the forces, or the net force, so I'm just going to leave that there for now. I know the mass of the child is 30 kilograms, and for that acceleration, I'm going to be thinking about my centripetal acceleration. And I could do v squared over r, but I don't know my linear velocity. However, I do know my angular velocity, so I can do omega squared times r. So I'm going to substitute in omega squared times r for that acceleration, and I know that my angular speed is 2, so 2 squared times my radius, which is 1.2. And so this is going to end up giving us a net force here of 144 newtons. For the second question, we want to know if the child were moved further away from the center, how would that affect their centripetal acceleration? And that would increase their centripetal acceleration. And the reason is, we see up here with this equation, centripetal acceleration is directly proportional to radius. So increasing the radius increases the centripetal acceleration. Alright, for this one, we have a centrifuge here that's going to start spinning around. That's what a centrifuge does, just a rotating disc. And we have a test tube placed in it some distance r from the center. So it starts from rest and reaches an angular speed of omega after a time t, and then maintains a constant speed until 2t. So we want to know when the test tube experiences a tangential acceleration. Well, it's going to experience a tangential acceleration when it has an angular acceleration, and that occurs from 0 to t. Okay, while the object is speeding up, it has a tangential acceleration, but once we hit t and maintain a constant speed, there's no more tangential acceleration. The next question asks, when does it experience a centripetal acceleration? Since the test tube is traveling in a circle the entire time, it's experiencing a centripetal acceleration, so that's from 0 to 2t. It doesn't matter if it's speeding up or traveling at a constant speed in a circle. If it's traveling in a circle, it has a centripetal acceleration. For C, we want to derive an expression for the magnitude of the net acceleration at the instant right before time t. So at that point in time, we're going to have a centripetal acceleration, and we still have a tangential because it's still speeding up to that speed of omega. So we want to calculate both of those. So for our centripetal acceleration, that's going to be equal to either v squared over r or omega squared times r. All right. We know omega, we know r, so that one is good. There's our centripetal acceleration at that point in time. We also, though, want to calculate our tangential acceleration. And in order to do that, I'm going to use the fact that tangential acceleration is r times alpha. However, we don't know our angular acceleration yet. So I'm going to go ahead and set up my angular kinematics. I start from rest, and I reach a final speed of omega after a time of t. So I can say omega final equals omega initial plus alpha t, and that means that omega is equal to alpha times t, and so my angular acceleration is just omega divided by t. And I can substitute that in for my angular acceleration here, and so I get that my tangential acceleration is going to be equal to r omega divided by t. Now the question asks for the magnitude of the net acceleration, and so I want to somehow combine these two, and what I notice is these two accelerations actually form a right triangle. That inward centripetal acceleration and that tangential acceleration form a right triangle. So I'm going to go ahead and I'm going to put those two accelerations together. So I'm going to have my omega squared r, which is my centripetal, and my r omega over t, which is my tangential, and I'm going to solve for that hypotenuse there using the Pythagorean theorem. So I'm going to go ahead and plug in those values for the a and b and go ahead and square it. So what I end up getting is omega to the fourth r squared plus r squared omega squared over t squared equals c squared. I'm going to end up pulling out an omega squared r squared, and so it's going to be omega squared r squared times omega squared plus 1 over t squared. This could be equal to c squared. And I can take the square root of both sides, and I find that my overall magnitude of my acceleration is just going to be omega r, because I can pull that out of the square root, times the square root of omega squared plus 1 over t squared. So that's what I'm left with for my magnitude. A little bit messy, but that's going to be our answer here to part C. For this last part here, we want to know if the distance from the center were doubled, will the magnitude of the acceleration be more than, less than, or equal to twice as much as the original. So my new acceleration, the new magnitude, a prime, is just going to be equal to, the only thing I'm going to change here is r. I'm going to make it 2r, okay? everything else, the angular speed and the time, stays the same. Right? And so when I go ahead and pull out that 2, I get that a prime is 2 times that original angular acceleration. So it's exactly equal to twice as much. And if we think about it logically, that makes sense because doubling the radius doubles my centripetal acceleration, and it also doubles my tangential acceleration. So if my x component doubles and my y component doubles, that overall magnitude is also going to have to double.